To calculate the length of a wire using its resistance, you'll need a formula and some key information. The formula is length in meters equals resistance in ohms times specific resistance in ohm meters divided by cross-sectional area in square meters. Let's break down the steps. Firstly, measure the resistance of the wire. Use a multimeter to accurately measure the resistance of the wire in ohms. Make sure your multimeter is properly calibrated for accurate readings. Secondly, determine the specific resistance. Consult Table 8, Conductor Properties, typically found in electrical engineering handbooks or online resources. This table provides the specific resistance, often denoted by the Greek letter ρ, of various conductive materials in ohm meters. The specific resistance is a material property that indicates how strongly that material opposes the flow of electric current. Different materials have drastically different specific resistances. For example, copper has a much lower specific resistance than steel, meaning it conducts electricity much more easily. Thirdly, measure the cross-sectional area. For a round wire, measuring the diameter is the easiest way to determine the cross-sectional area. Measure the diameter, denoted as d, of the wire in millimeters. Then calculate the cross-sectional area using the formula area in square meters equals pi times d divided by 2 squared times 10 to the power of -6. The 10 to the power of -6 factor converts the area from square millimeters to square meters. If the wire is not round, you'll need to determine its cross-sectional area based on its specific shape. For example, for a rectangular wire, you would measure its width and height and multiply them to find the area. Now apply the formula. Substitute the measured resistance, the specific resistance obtained from Table 8, and the calculated cross-sectional area into the length formula. Perform the calculation to find the length of the wire in meters. Now let's consider an example. Suppose you measure the resistance of a copper wire and find it to be 5 ohms. You consult Table 8 and find that the specific resistance of copper is approximately 0.175 ohm meters. You measure the diameter of the wire to be 1.2 millimeters. First, calculate the cross-sectional area. The area in square meters equals pi times 1.2 divided by 2 squared times 10 to the power of -6, which equals approximately 1.13 times 10 to the power of -6 square meters. Next, substitute the values into the length formula. The length in meters equals 5 ohms times 0.175 ohm meters divided by 1.13 times 10 to the power of -6 square meters, which equals approximately 77,000 meters. Therefore, the length of the copper wire is approximately 77,000 meters. A few important notes. This formula assumes that the wire has a uniform diameter throughout its entire length. If the diameter varies significantly, the calculated length will be an approximation. Ensure you use the correct specific resistance value for the wire material in question. Using the wrong value will lead to an inaccurate length calculation. For wires with non-round cross-sections, accurately measure or calculate the cross-sectional area based on the wire shape. The formula is derived from Ohm's law and the relationship between resistance, resistivity, length, and cross-sectional area. Resistance is directly proportional to length and inversely proportional to cross-sectional area. The specific resistance, or resistivity, is a material property that accounts for the material's inherent ability to conduct electricity. The units must be consistent. Ensure that all measurements are in the correct units before performing the calculation. If the diameter is measured in inches, convert it to meters before calculating the area. The formula can be rearranged to solve for other variables such as the specific resistance or cross-sectional area if the other parameters are known. For example, if you know the length and resistance of a wire, you can calculate its specific resistance. The accuracy of the calculated length depends on the accuracy of the measurements. Use high-quality measuring instruments and take multiple measurements to minimize errors. Temperature can affect the resistance of a wire. The specific resistance values in Table 8 are typically given at a specific temperature, usually 20 degrees Celsius. If the wire is at a significantly different temperature, the resistance value may need to be adjusted. The formula applies to DC resistance. At high frequencies, the AC resistance of a wire can be higher than its DC resistance due to the skin effect. The skin effect is a phenomenon in which alternating current tends to flow near the surface of a conductor, reducing the effective cross-sectional area and increasing the resistance. For a stranded wire, the overall resistance will be slightly higher than that of a solid wire of the same material and dimensions due to the increased surface area and the presence of air gaps between the strands. Consider using a 4-point probe method for more accurate resistance measurements, especially for low resistance wires. This method eliminates the effect of lead resistance on the measurement. Understanding these concepts and applying the formula carefully will allow you to accurately determine the length of a wire using its resistance. In summary, firstly, accurately measure the wire's resistance using a multimeter. Secondly, identify the wire material and find its specific resistance in the conductor properties table. Thirdly, determine the cross-sectional area of the wire, either by measuring its diameter for round wires or by direct measurement for other shapes. Finally, plug these values into the formula length equals resistance times specific resistance divided by cross-sectional area to calculate the wire's length. Pay close attention to units, ensuring consistency to obtain an accurate result. Always double-check your measurements and calculations to minimize errors. Remember that factors like temperature, wire type, whether it's solid or stranded, and frequency of the current can influence the accuracy of your results. By following these steps carefully and considering these factors, you can confidently determine the length of unknown wires in your shop or laboratory.